So basically on radioactivity, this is going to be important when we do brachytherapy, which basically uses radioactive sources. So just to cover the background is important, so that once we get there, we won't have to repeat the same things. All right, so basically in radioactivity, it's a process in which an unstable nucleus basically decays to a daughter nucleus, which can either be stable or unstable. All right. So if an unstable parent decays to give a daughter, the daughter can further decay into a granddaughter nucleus. Okay. And this would continue to occur until a stable configuration or a steady state is achieved. All right. So it can be a series of decays from parent all the way to the ground state configuration. All right. It was discovered in 1896 by Henry Becquerel, and there are many other names that are used to describe radioactivity. So depending on the text, sometimes it's called nuclear decay, nuclear disintegration, nuclear transformation, nuclear transmutation. But the most common term, I believe, is radioactive decay or nuclear decay. All right. But in this course, we will mostly use the term radioactive or nuclear decay. Yeah. The other terms, not so much. All right. So, like I said, it's a transition from an energy state of a parent P to another energy state of a daughter D. All right. And of course, the energy difference between those two energy states would be called the decay energy Q. All right. That decay energy Q between the parent and the daughter can be released in the form of electromagnetic radiation or photons, which are specifically in this case called gamma rays. All right. Because these are emitted from the nuclear decay. So these will not be like X-rays. So these are specifically gamma rays. All right. It can also be emitted in the form of the kinetic energy of the product. All right. So it can either be emitted as energy or gamma ray energy or kinetic energy of the products. All right. And of course, we can govern these processes based on the decay constant. And we have defined activity before as just the number of radioactive nuclei at time t. All right. So, sorry, it's basically the decay per unit time. But we can actually form an equation between the decay constant lambda and the number of nuclei that are present at any given time. So it's simply the decay constant is in the units of per second. All right. And of course, this is a number. So activity would be basically the number of nuclei decaying per unit time. All right. Actually remaining per unit time. All right. The specific activity is basically the activity per unit mass, and we can further break that down to the level of the Avogadro's constant and the mass number. All right. I'm not going to go through how we can derive that. You can go through that on your own. But specific activity basically is the decay constant times the Avogadro's number, which is basically 6.023, I think, times 10 to the power 23, divided by the atomic mass number. Okay, so this would depend on the actual atom we're looking at. For cobalt 60, of course, that would be 60. All right, so like I said, activity is the number of decays per unit time. So that's why it's represented by becquerel, which is per unit time, right? Decays per unit time. That's basically what activity is. All right, I showed you before that becquerel is can be related to the Curie, which is the older unit. All right, so Curie is a much larger unit, so it's equal to 3.7 gigabecquerels. All right, and it was originally defined as the activity in a gram of radium-226, which is basically about 1 curie, all right, or 0.988 to be specific. All right, so let's look at how we can derive the exponential decay equation. Again, I'm not going to be deriving this equation. I believe it's simple mathematics. All you need to do is to express the rate of depletion of the parent with the activity, right? So we have defined the activity already to be equal to the decay constant times the number of nuclei, all right? So we can take this equation and introduce integral signs, right? Remember, integration and differentiation, these are like opposite operators. So once you integrate this and the left-hand side and the right-hand side, then you can come up with the exponential equation. Of course, you put in the limits from 0 to time t, all right? And from NP0, all right, number of particles at time 0 to the number of, so not number of particles, sorry, but the number of nuclei of parent at time 0 and at time t. Once you plug in those integral limits, then you can obtain the exponential equation, right? I think this is undergraduate type of physics. And you can apply the same to the activity. So remember, the number of nuclei and the activity can be related through this equation. So you simply have to multiply by the lambda, and then you get the activity from the number of nuclei. All right. So the same equation applies to the activity. If you plot that, of course, you get the exponential equation, which I'm sure you might have seen before. And the initial activity would be A0, of course, and then it begins to decay exponentially all the way. Of course, it never reaches 0, but of course, we can define certain terms like the half-life, the mean life, the half-life being the time it takes for half of the original activity or the nuclei to decay. Right? So it corresponds to, so T half corresponds to half of the original amount. All right, so if you put A over 2 here, you simply have to extrapolate to the, and then you get the half-life. The mean life, on the other hand, is basically the amount or the time, sorry, that is needed for the activity to reduce to 1 over E. Okay, remember half-life corresponds to 1 over 2 of the original activity. The mean life corresponds to 1 over E, whereas E is the exponential, the one that I think is 3.1. Let me see if I can calculate it here on my computer. What is the value of E for anyone who knows? I don't know if I have a scientific calculator here. 2,718. All right. All right. So the mean life is basically the amount of time needed for the activity to drop to 1 over 2,718. All right. So that's the mean life represented by the symbol tau. All right. I've already defined this. So half-life is the time for the number of nuclei to decay to have the initial value. All right. From the initial, remember you have to start at t is equals to 0. So from the initial value, all right. And you can relate the half-life to the decay constant through this equation. So basically the half-life is ln 2 over lambda, or lambda is equal to ln 2 over half-life. All right. Again, this is basic equations, and I'm not going to be wasting too much time on these things. Now let's look at a serial decay series, right? A serial decay scenario where we have got a parent decaying to a daughter and a daughter further decaying also to a granddaughter, okay? So we have got 2 unstable nuclei, So the parent is unstable, and then it decays to a daughter, and then a daughter is also unstable, and then it decays further to a granddaughter. All right. So we can basically form an equation based on this scenario. We know the parent simply follows as an exponential decay. All right. The daughter, on the other hand, we know that it's going to be a difference of the formation from the decay of a parent and the decrease from its own decay. All right. So in other words, the daughter is being formed from parent decay. And on the other hand, the daughter is also decaying itself. So the daughter actually has a formation from the parent and it's also decaying. All right. So this is the rate of change of the daughter. All right. What I want you to do is to derive this equation here. I want you to try and derive this equation here, and we'll try to do it together. But or I can give you like a little right. So I'll give you like a little hint. So you have a parent decaying to daughter and a daughter decaying to granddaughter, right? So of course, the parent is a decay constant lambda p, the daughter with decay constant lambda d. So these two are radioactive. The granddaughter is stable. All right. Like I said, the parent is not being formed from any other decay. So it simply follows an exponential decay equation. All right. So the rate of change of the parent with time is simply the initial amount times the exponential decrease. All right. Whereas the daughter, on the other hand, is being formed from the parent and it's also decaying. All right. And we can transpose this and put it on this side. So we can move this part and put it here. And then we end up with this equation. But we know that the parent is actually just follows a normal decay, right, like this. So we can just substitute that here. And then we end up with this equation. Now, once you have this equation, the trick here is to multiply by this exponential function. And the reason for that is we know that for those of you who are good with calculus, for those of you who have done integration and differentiation, maybe in your undergrad or in your, your GSCE, your high school A level or whatever, you may have done differentiation, and you know that if you have a function which is a product, you can actually differentiate it by parts. So this part here, if you multiply the left-hand side with this function, what you end up with is you will know that the left-hand side, after multiplying with this part, would be equivalent to the differential of this component here. So that is where the trick is. All right. And once you figure that out, you simply now substitute this whole part with a differential. Now it reduces to this. And you know, if you integrate a differential, those two cancel out. Remember, differentiation, integration, these are like opposite, these are like opposite operations. All right. So the differential and the integral will cancel out and you'll remain with this. But of course, you have to input the limits. All right, that's where the trick is, really. And the rest will just be working out the mathematics, and then you end up with this equation. Not the difference here between, I just want to show you something here. If you check this equation that I worked out in blue, all right, you have got a second component here, rather a third, because we have two here with this component and this component. There's a third component here, which is actually dependent on the initial amount of the daughter. All right. So remember, we're starting with the parent, and then to daughter, and then granddaughter. So normally we assume that there was no daughter nuclei in the beginning. So we normally assume that it was 0 initial. Where was I? We normally assume that this part was 0. So there were no daughter nuclei in the beginning. All right. So all the daughter we have originated from the parent. So we have no initial amount. So that is why you see this equation here does not have that component. But if there's a question which gives you an initial amount, then you need to include this part. Otherwise, this equation assumes an initial activity of 0 of the daughter nuclei. And of course, you can extend from the number of nuclei to the actual activity by simply multiplying by a lambda, and then you get to the activity. All right, making sure that if you multiply the parent, this would be A, right? Lambda P times NP would give you A. All right, so I want you to derive that equation, and please send me what you have, right? You can use the internet, you can use whatever method you want, but this will help you to basically understand the whole serial decay. All right. So are we together on so far? Please let me know in the chat if we are still together. So your homework is just to derive this, all right, from this equation. Start here. In fact, I would want you to like start from here and then just to explain the steps. All right, just to show you understand this whole thing. All right. So derive this and include the part that I showed you. All right. Don't assume the initial daughter activity is 0. So include that third component. All right, and of course you can extend to activity from number of nuclei. You can go extend to the activity, and you can plot both on the same axis. Of course, the parent will follow the simple exponential decay. All right, so this will be like the same exponential decay that you know. All right, whereas the daughter starts from 0. Remember, we said there was no daughter in the beginning. So the daughter starts from what? From 0. So that is the reason why when you look at the daughter, it starts from 0 here. And then it rises up. All right? When the parent is decaying, the daughter is increasing. And then it gets to a point when the parent and the daughter are the same. All right? When they are the same, we know that the rate of change of the daughter activity will be 0 because it maxes out and it gets to a plateau where the tangent is actually 0 of this curve. So we know the tangent is 0 when the differential is 0. So at that point, we know dA dt is 0. All right. And once you do that, meaning if you differentiate the daughter activity, you should get 0. All right. Meaning if you differentiate this and equate to 0, and so for time, you end up with the value of t. In other words, the time at which this occurs, at which the daughter maxes out. All right. So once you solve this differential, you end up with this equation here. T max. All right. So this is the time at which the daughter activity is at the maximum. All right. Now we have 3 special considerations for this type of decay. The first case is when the half-life, you can discuss this, of course, in terms of the half-life or the decay constant. Okay. So you know the two are inversely proportional. All right. So when we say the daughter decay constant is less than the parent, the time or the half-life would be vice versa. All right. So if it is less here, it will be more here. So the first case is when the daughter half-life is greater than the parent. In this case, there is no equilibrium at all. All right. And you just have this general equation that we had earlier on. Now, the second case is when the daughter activity is now less than the parent activity. All right. In this case, we have what we call transient equilibrium. All right. I want you to also look at what the graph for transient equilibrium looks like and what the graph for secular equilibrium looks like. This is more applicable in nuclear medicine. All right. So I don't know, Mr. Jason, when he takes you through medical imaging, he's going to probably explain this. But this is important in nuclear medicine. So I'm just giving you the basics here. And of course, in brachytherapy, we also deal with radioactive sources. All right. So just be careful and make sure you understand these concepts. You have access to all the books and the internet to be able to explore these. But here I'm just giving you a summary of these three scenarios. So no equilibrium. In this case, now we have got, so no equilibrium exists if the daughter is greater. All right. If the daughter is greater, there is no equilibrium. But once the daughter is less, then we get transient equilibrium, okay, in terms of half-life. Now, there is a third scenario when the daughter is much less than the parent. Then you get secular equilibrium. All right. And of course, the corresponding equilibrium formulas are given here on the right side. All right. So I'm not going to go deep into the mathematics of those concepts or the physics of it. For now, we just have to acknowledge the conditions under which each circumstance would occur. Okay. So there are three special conditions: no equilibrium, transient equilibrium, and secular equilibrium. All right. It's another thing which I would just want to briefly point out is radioactivation. All right, or thermal activation of neutrons. Basically, this occurs if you bombard a target or a parent nuclide in a nuclear reactor with thermal neutrons. All right, that would actually transform that nuclide into a daughter nuclide. All right, so similar to a serial radioactive decay, if you bombard a parent with thermal neutrons, then you would get a daughter. All right. And that daughter usually would actually be unstable and would give you a granddaughter. All right. So this is like an artificial way of creating radioactive material. All right. So the probability of for that to occur, for radioactive activation to occur, is actually determined by the cross section. All right. So the cross section, I think something moved here. I just want to, let's see. I'm trying to move this thing here. It looks like that. All right. So the cross section with that symbol sigma would actually determine the probability for this process to occur, and it's given in the units of barns, right? And one barn is basically 10 to the power minus 24 square centimeters. So it's actually like an area. All right, it's a cross section, so it's like in the units of like area, and the neutron fluence rate is basically the it's given by these units here per square centimeter per second. But I'm not really going to test you on these kinds of things, but I just want you to take note that you can actually create these unstable nuclides through thermal activation or through bombardment in a nuclear reactor. Right? And this is actually done practically. And I'll show you an example of cobalt-60. But you can actually form an equation similar to the one that I just asked you to derive for the activity of that daughter. Okay? Remember, you bombard this parent and then you get a radioactive daughter. All right? And you can calculate the activity of that daughter through a similar process for what we did earlier on, right? And you get this formula for the activity of the daughter. Okay, and of course that activity depends on the cross-section, sigma, and the nuclear fluence rate. All right, what is the neutron fluence rate? It's basically the number of neutrons that are being bombarded per unit area, per unit time. All right, that's the neutron fluence rate. So the number of neutrons bombarding that target per unit area, per unit time is the fluence rate. All right. So our activity will depend on that, and also the probability of the cross-section. All right. And of course, you can derive the Tmax just like we did with here. We can do the same thing, and you can get a Tmax as well, at which the daughter would reach the maximum activity. Okay. An example of how that's done and why that's important is because in radiotherapy, sometimes, I'm not sure how many, I think a lot of teletherapy facilities that use radioactive sources, they use cobalt 60. Some of them are used in the past cesium-137, but I think that was, it's no longer in use in most facilities. So we need cobalt 60 for cancer treatments using gamma rays. So that's how, and we'll discuss this as well when we discuss sources of these radiations in clinical radiotherapy. So cobalt 60 is one of the most popular in teletherapy or in external beam radiation therapy using gamma ray sources. Remember, we can do treatments using X-ray beams from linear accelerators, and we'll discuss those machines as well. So linear accelerators, basically, they can produce electrons. They can also produce photons, but these would be X-ray photons. If we want to use gamma ray photons, then we can actually create cobalt 60 using this process here that I showed you before, through thermal neutron bombardment of cobalt 59. So you take cobalt 59, which is a stable atom, and if you bombard it with thermal neutrons, then you can actually create cobalt 60. And cobalt 60 actually emits gamma rays that you can use for treatments. All right. And this reaction has got a cross-section of about 37 barns per atom. And in terms of the nuclear fluence rate, remember we said earlier on that it depends on these two, the cross-section and the number of neutrons per unit time, per unit area. So for this scenario here, the cross-section is 37 barns, and the typical fluence rate for neutrons here would be about 10 to the power 14 neutrons. So that's a lot of neutrons that are being bombarded per unit area, per unit time. All right. Are we together so far? You can let me know in the chat. Yes. Right. Good. So let's look at some of the modes of radioactive decay. And I'm sure this is something also you may have covered before, but I'll just give you a run through quickly. So basically in radioactive decay, we've got an unstable nuclei that decays to form a more stable nucleus, all right, or even a ground to like a ground state configuration, right? So there's four main modes: alpha decay, beta decay, gamma decay, and spontaneous fission. All right. And on beta decay, as you know, there's beta plus, beta minus, and there's also electron capture. All right. Gamma decay also is further divided into two, which can be just pure gamma decay or internal conversion. All right. So let's quickly look at these modes of radioactive decay. All right. So in terms of the decay products, in alpha decay, as the name suggests, of course, you emit alpha particles. An alpha particle is basically the nucleus of a helium atom. All right. So That's alpha decay. Beta plus would obviously produce a beta particle, which is a positron or a positively charged electron, and a neutrino. Beta minus would give you just an electron, or just a beta minus particle is just an electron, and an neutrino, which is like an antimatter to the neutrino. All right. So as you can see, beta plus and beta minus, they produce antiparticles to each other. So beta plus and beta minus are antiparticles. Neutrino and antineutrino also, this is also antimatter, matter and antimatter, right? Electron capture produces a neutrino. Pure gamma decay produces photons or a gamma ray. Internal conversion also emits orbital electrons, all right? Whereas spontaneous fission would give us a fission products. Okay, that depend on the actual fission atoms that are involved. And of course, there's conservation of physical quantities like energy, momentum, atomic number, and charge. Right, you can calculate the decay energy, which we sometimes call the Q value. All right, so if you have a parent P that is decaying into a daughter D, all right, you can actually calculate the decay energy. All right, and the decay energy will be given by this equation, basically. All right, so MP is the rest mass of the parent, MD is the rest mass of the daughter, and then small m is basically the mass of the particles that are emitted. And of course, you multiply by c squared. Remember, mc squared, E is called mc squared. So E will be equivalent to the Q because it's the energy. M, so these are the M particles that you basically subtract the parent minus the parent minus the daughter or the products, all right? And then times c squared to convert to the energy. All right, so this represents E equals mc squared. Right, alpha decay, as we know, it produces an alpha particle. An alpha particle basically is a helium nucleus, all right, which is a mass number of 4 and an atomic number of 2. So we expect the daughter to decrease in mass by 4 and the atomic number to decrease by 2. All right, straightforward. An example is the decay of radium-226 to radon-222. All right, so radium is a mass number of 226 and an atomic number of 88. This would decrease by 4 and this would decrease by 2. So this would be 222 and 86. So if you look up on the periodic table, that would correspond to the atom radon. All right, and of course there's an alpha particle, which is a helium nucleus. Radium-222 is a half-life of 1,600 years. Beta plus, of course, beta plus gives us a positron or a positive electron and a neutrino. The atomic number of the daughter basically decreases by 1. All right, I'm not going to waste time here. I know you do atomic and nuclear physics, so I expect that to be covered in that course. An example of that would be the conversion of nitrogen-13 into carbon-13. All right, so the mass numbers remain the same, but the atomic number decreased by 1. Okay, so if you look up on the periodic table, you will have an a carbon-13. All right, a carbon-13 is like an isotope of carbon. All right, and of course you get an electron, which is positively charged, or a positron, and a neutrino. Beta minus is just like the opposite. So instead of the atomic number decreasing by 1, the atomic number actually increases by 1. All right, the mass number remains the same, and instead of having a positron here, you have an electron. All right, or a I think it's sometimes called a betatron. All right, and instead of having a neutrino, now you have an anti-neutrino. All right, so this is beta minus decay. An example of that is cobalt-60 decaying to nickel-60. Mass numbers remains the same, but the atomic number increases by 1. from 27 in this case to 28. And the electron and the antineutrino are products of that. All right. In terms of electron capture, in this case, basically, an electron is captured by the orbital. Sorry, a nucleus captures an orbital electron. And this electron is usually like in the K shell. So what happens is a proton transforms then into a neutron and you eject a neutrino. All right. So now since a proton transforms into a neutron, what happens? The proton number decreases. Remember, a proton transforms into a neutron, right? So the proton number, which is the Z number or the atomic number, decreases by 1. All right. So you absorb an electron and you eject a neutrino, but now your atomic number decreases by 1, just like beta plus decay. All right. Right. An example of that is beryllium-7 transforming into lithium-7. All right. So beryllium-7 basically absorbs an electron, and then the proton is converted into a neutron. And so the atomic number decreases from 4 to 3. All right. And if you look up in the periodic table, the atom which corresponds to a mass number of 7 and an atomic number of 3 is lithium. All right. How about gamma decay? Gamma decay basically is a nuclear decay in which a parent is produced. All right. And of course, we can produce gamma rays from alpha decay, beta minus decay, or beta plus decay. All right. So examples of gamma decay, we can have cobalt-60. Remember, I gave you an example of how cobalt-60 is formed, right? Cobalt-60 is formed by neutron bombardment of cobalt-59 in a nuclear reactor. Cobalt-60 is unstable, so it decays into nickel-60. So you have cobalt-59 here being bombarded, you get cobalt-60. Cobalt-60 decays naturally into nickel-60, right? That process emits, so that process is occurs by beta minus decay. And then the radium 226 also decays into radium 222 by alpha decay. So this is an example of radium to radon. This is an example of cobalt-60 to nickel-60. All right. And by the way, in the decay from cobalt-60, there is actually 2 gamma rays that are emitted. 1,173 and 1,332 gamma rays that are emitted. All right, but we're not spending too much time on these things. I'm just highlighting some of these things that we may encounter when we do brachytherapy. All right, so I figured instead of me just jumping into interactions, I should go back to the basics first. Internal conversion. All right, what happens during internal conversion? Well, what happens is that the de-excitation energy, so when a nucleus is de-excited from a high energy state to a low energy state, that energy, instead of being released, is now absorbed internally by an orbital electrons, usually a K shell. And this energy now emits that electron. All right. So that electron is now emitted with a kinetic energy, which is equal to the de-excitation energy minus its binding energy. Remember, every electron is bound to the atom by the nucleus. All right. So that binding energy will keep it in orbit. So whatever the de-excitation energy is, it has to overcome the binding energy. So the energy of the ejected electron would be equal to the difference between the binding energy of the electron and the absorbed or the internally absorbed de-excitation energy. All right. Now, obviously, once that K shell electron is ejected, it leaves a vacancy. All right. This vacancy is then filled by an electronic transition from a higher energy state Remember, lower energy states have to be filled first, right? And then in that order. So the K shell would be filled first, and then L shell gets filled, and then M as you go out from the nucleus. So that internal vacancy, or let me say that innermost vacancy, is filled by electronic transitions from higher energy state. Now what happens is now that those transitions will give characteristic photons, which are which are X-rays formed due to the transitions of electrons from higher energy levels to lower energy levels. So these photons actually have got energies equal to the difference in those binding energies. All right. So just to summarize here, the de-excitation energy, instead of being released, is internally absorbed. Once it's internally absorbed, it knocks out an electron from an inner shell, like a K shell. That electron vacancy is then filled in by outer electrons that occupies that vacancy. And the energy difference between the outer electrons and the vacancy binding energy is now, is the energy difference is ejected as characteristic photons. By the way, I just want to know if anyone here knows why those photons are called characteristic. What do they characterize? Does anyone know? If you don't know, you can type no. Why are these photons called characteristic photons? If you don't know, type no. Okay, radio says no. All right, no, 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 no. All right. So basically every atom has got a signature. So every shell in an atom has got a fingerprint. So these binding energies in every shell, they're actually like fingerprints. So let's say tungsten, all right? Tungsten with an atomic number of 74. I can't remember the binding energy of tungsten. I think the binding energy of tungsten is 69 point something. Right. So that becomes the signature of tungsten. So if an electron moves from an outer shell, let's say with a binding energy of 23 to an inner shell with a binding energy of 60, 69, whatever, then the characteristic photon ejected would have a binding energy equal to the difference. So let's say 69 minus 23, that would give you what? 40 something. All right. So that would be characteristic of tungsten. It's like a fingerprint of tungsten. All right. So that's why it's called characteristic. It characterizes a particular atom. All right. Auger electrons are electrons which are ejected. So now, instead of those characteristic photons being released, they may be absorbed again internally and eject electrons, which we call Auger electrons. All right. So an electron transition occurs and then characteristic photons are formed. Those photons, those characteristic photons can eject an outer shell electron, which we will call an Auger electron. So what's an Auger electron? In short, an Auger electron is an electron that is ejected from an internally absorbed characteristic X-ray. So a characteristic X-ray is not emitted, but it's absorbed, and it ejects an Auger electron. All right. So internal conversion can lead to a cascade of, other processes. As you can see here, there's a lot of things that can happen just from one internal conversion process. All right. Now you see there's characteristic photons, there's Auger electrons. You see? Right. An example Of course, an example of conversion electrons, internal conversion electrons, would be cesium-137 being converted into barium-137. And of course, the half-life of barium-137 is 30 years. All right, that's one example. Lastly, spontaneous fission, it basically occurs when a nucleus splits into two fragments. All right, and these fragments would be nearly equal. All right, so normally there's 2 to 4 neutrons that are emitted during this process, during fission. And this again is a nuclear physics type of topic, so I'm not going to waste time on that. I want us to jump into more relevant material here, which is basically interactions of electrons with matter. All right.